Next, we have 3 student presentations. The story is that we did not have very clear process how to select student presentations, and I can convince that there was some supervisor involvement in those cases. So Novin Sharodi first, please set up. So he's supervised by Meelis School and in topic related to uncertainty. Next, setting up is Hele-Andra Kuulmets on NLP topics. And last not least, Taavi Kivisik, supervised by Anna Aru. But Novin.
Okay, so yeah, I'm Novin, PhD student in Machine Learning Research Group, supervised by Meelis School. Today I'm going to talk shortly about marginal distributions and beyond that. So I start with forecasting task because it makes a good use case or case study for what I'm going to talk about. But as I started, let's look at the regression task. So in regression, you're aiming at finding a relationship between a dependent variable y and independent variable x, known as feature and target usually in machine learning community. And so we find like a relationship that could look like a linear line as such, fit it to the data. And in time series forecasting task, we have x-axis time and y-axis target variable to find a relationship for. And it could be thought of as a regression task. So many independent regression tasks that are independent, like for each time step. So now we not only have like x as an independent variable, but t as independent variable as well. So basically, we turn the features into time features. Basically, we have independent time features, and we also need a stationary data. So that's a recipe to get like IID time series that is essential for running any regression task for any regression model on the time series data that we have. So basically formulating everything as a regression in time series. But what makes time series different then, if it's just doable with the regression or with the same setup as a regression? So in time series, we stand at the present time and we aim to forecast the future. We usually have a bunch of past data, historical data, which we usually look at a certain window of that historical data, and we have also some future features that could exist or not, but could exist and help our prediction about the target variable y. The essential thing in time series is that we have dependent, time-dependent and time-independent features, and we're aiming at basically capturing these time-dependent, aiming to capture these time-dependent relationships. So the variables are evolving through time. Now, I briefly look at different forms of forecast because it's essential to the gist of the talk. So we have point forecast, which is the most common form of forecast. It's a mean prediction. So basically, the forecaster or the model that we have provides the mean of the underlying distribution associated to the y variable, conditioned on the fact that we're using a certain family of model denoted by G. Information set, basically the training data we have, and then optimal or suboptimal parameters of the model that are estimated. What is important is that this type of prediction only informs us about the mean of the underlying distribution and basically informs us for each time step independent of one another. Taking a step further, we have quantile forecast. It provides more information in terms of probability. So it's informing us about the certain quantile of the underlying distribution, such as the 50th percentile corresponding to the median of the underlying distribution. If we take it another step further, we can have quantile prediction in such a way that we can create actually prediction intervals. So the lower bound in this prediction interval corresponds to, for example, in this case, fifth quantile prediction, a 5th percentile, and the upper bound corresponds to the 95th that all in all creates this 90% prediction interval and informs us about more things, such as the fact that the true value should lie between this interval 90% of the times. And the more confident the model is, the sharper the interval would be, the width of the interval. And if we put this, extend it to a case where we have like infinitely many quantiles predicted, then we can get such fan chart, so-called fan chart, that's essentially estimating the density of the underlying distribution. And well, one way to look at it is in terms of quantum prediction. So basically the model learns the inverse CDF of the underlying distribution. So many different quantals are inquired from the model and learns this inverse relationship. In effect, we are able to represent the distribution of the underlying variable, either in terms of PDF or CDF, doesn't matter. What is common among all these types of forecasts is that these forecasts are informing us marginally about the data. So marginal in terms of like time steps. So this distribution predicted or represented by the model is only about one of the time steps in this forecasting setting, and so on and so forth for each of the time steps, so independently of one another. But there could be also another alternative. The alternative is to inform also about the dependencies in the time. So that's where I get to the gist of the talk, which is about joint distribution of the data. So a smaller example, more understandable. So here we have two variables, T1 and T2. So we can see the marginal kind of prediction for time step 2 and time step 1. So each of these marginal distributions could also, like the model could alternatively, instead of predicting the marginals, could also predict the joint distribution, which is this kind of object in the middle. So not only we have some information about distribution per time step, we also have some information about how these two time steps interact. So in some other sense, correlation between the time steps. And another way to depict it is as such. So here we have like a two example, same one. So we have a multivariate Gaussian distribution here, marginally shown this red curves, and also samples from this multivariate distribution, which could also be called as a scenario forecast in the setup that I showed you in previous slide. But what is it about this joint distribution that is important? So there is some information lying in this joint distribution, and I'm going to make it a little bit clear with another toy example. So now we're looking at the marginals in terms of a kind of a discrete representation. Each box, basically, here is kind of a mass in the support of the marginal distribution. And now I would like to suggest looking at it, at the information that lies in this joint setup in terms of a transport plan. So if you take just one column from one of the marginal distributions, what are the different ways we can actually transport this mass into this joint space? And you can think about so many different ways that this could occur. So essentially, if we think about all different transport plans that could occur, if you think about different columns, then there are so many different degrees of freedom in terms of like how we can construct a joint distribution based on marginals. And so why is it important at all? I'm going to skip a couple of slides. Maybe in the discussion part we will get back to it for the sake of time. But why is it important? Because like if you think about it, like in some settings, we basically need the model to learn this joint information. Like this plan is unique or supposed to be unique. I want the model to find it. And I give some examples of the applications. I would indicate that is indeed needed in some applications, if not many. So this is an overview of different forms of forecast we looked at. And so we have basically scenario forecast as like kind of a way to represent multivariate distributions in a kind of Monte Carlo fashion. So we have samples of this underlying multivariate distribution. So applications, there are so many emerging applications. The more we go into real scenario, kind of real world examples, the more it becomes of an essential thing to have this joint distribution modeling or methods for that, multivariate analysis. And so, for example, in energy sector, we have renewables due to a stochasticity of renewable energies such as wind, solar, so on and so forth. And kind of the dependencies between basically the observations that we have from the wind and so on and so forth makes it essential to be able to model these dependencies in order to be able to have a more optimal decision making in terms of, for example, balancing the grid and downstream tasks. We have autonomous cars. Trajectory prediction is a good example of how these joint information are important. Could happen often in so many applications that we actually train a model marginally, but employ it and deploy it basically in a setup that actually requires joint information captured and also represented in the output of the model. A couple of other examples I'm going to skip for the sake of time. Another example I have in application, this is like kind of a testament to the importance of this matter. So in reinforcement learning, we have, in this paper, authors compare different models, different agents that are marginally almost identical. So in terms of accuracy, expected calibration error, which is a marginal kind of a score to show us performance of the model. So they're marginally almost identical. Scale divergence for the first time step in this kind of reinforcement learning agent, which makes decision through time, is also almost identical. But when we look at the trajectory of the agent, like in 10 time steps, it varies. So all these identical, seemingly identical models, actually they are so much different, and they make decisions differently, and the time matters, and these dependencies matters. So I conclude with this slide that for every prediction, a decision awaits downstream. So all the forecasting models, prediction models that we use, we employ, basically are going to be used somewhere in some downstream task. And maybe the most important observation is that we often evaluate and train these models marginally. And there has been more emphasis on models with more capacity to capture this kind of joint information, but less emphasis on the output representations of these models to be able to give us a good representation in terms of assessment and in terms of using it to provide a better learning signal for the model. So thanks, and we are ready for any questions.
Yes, we are ready for any questions, please. That was quick.
So I can use this time to throw some controversial statements so that it will raise a little bit of a tendency.
Yes, please, one controversy.
So, well, this is not maybe, well, let me make two claims. One controversial, one not so much. So in the beginning, I mentioned about the IID setup. So like it can happen that like we have so many stricting assumptions when we deploy models in reality. We train them with some assumptions and like in laboratory, but when it goes in the wild, into the wild, these assumptions are carried away with them, such as the independence of the time steps, for instance, is one of them. Well, in time series forecasting is more obvious, it's more explicit because this time dependency is like an essence of the problem. But we have also other setups that these dependencies may be a little bit hidden. For instance, I don't know, think about MNIST, like, or think about self-driving cars. Like, yeah, okay. But I'm still like on the, I thought I'm on the time, but yeah, let me cut it here. So I would claim that, for instance, for the self-driving cars, to be able to actually improve these 2-3 decimal points a little bit better, higher accuracy, maybe it's the thing that we are not looking at the joint information, and we're missing it, and the fact that you're only evaluating marginally, if you're kind of missing the point or missing some information that is essential of getting better.
Thank you. Thank you to passionate Novin.
Hi everyone, can you hear me? So my name is Andra, but you can call me Hele. I am a second-year PhD student here in the Institute of Computer Science in Natural Language Processing Research Group. My topic for today is using machine translation to solve Estonian natural language understanding tasks, because it's something I've been recently working on. My whole talk today will base on experiments done on the COPPA task, which is a small but quite popular natural language understanding dataset for evaluating language models. So the problem that NLP people who work with non-English data often face is that they have no data. And I have seen people, including myself, not gonna lie, get stuck here because you can't do anything without the data. Of course, you could always hire a group of people and ask them to grade the data for you, but it's expensive and doesn't guarantee you success with your task anyway. On the other hand, there's a lot of data, probably even for your specific task, available in English, so which you could make use of, so why not do it? The obvious way to do it is, of course, with machine translation, which means that you will either machine translate more data to Estonian to train your model on Estonian, or you could machine translate your Estonian data to English to train or reuse models trained on English. The first method is also sometimes called translate train, while the other one is called translate test. So before I'm going to actually present you the results of some of the experiments, let me maybe describe you real quick the COPPA dataset on which the experiments were done. The name stands for Choice of Plausible Alternatives, which is a common sense causal reasoning task. The original dataset is in English, of course, but there exists a cross-lingual version of it that contains professionally translated development and test datasets for 11 languages, somewhat surprisingly, including Estonian. The task itself is given a premise and 2 alternatives to select the alternative that more plausibly is either the cause or effect of the premise. For example, if the premise is that the woman repaired her faucet and you have to pick a plausible cause for this, then the answer would probably be that the faucet was leaky. And most probably she didn't repair it because the faucet was turned off. The task is usually formulated as a binary classification task, where the premise and one of the choices is concatenated, and the model has to predict whether that cause or effect is plausible or not, that is true or false. Now, going back to the experiments, the goal of the experiments was to find out how different approaches for grading training data will affect the performance of the model. And whether is it true that better data in terms of quality implies better results, that is higher accuracy in our case. The training datasets, therefore, are listed in the slide. Firstly, simply machine-translated data. Secondly, machine-translated and manually post-edited data, which is more expensive, but the quality is probably better than machine-translated data. And thirdly, mixed machine-translated and English data that gives us basically 2 times more training data. And of course, development and test sets were fixed, and they were in Estonian in all the experiments for Translate Train. So about the results. Some results are surprising, the others are maybe not. By the way, the names on the x-axis in the figure refer to different language models. Don't worry if you don't know them, it's not relevant right now anyway. Just that the first 2 are Estonian language models, which means that they are trained on Estonian, and the other 2 are multilingual language models trained on many different languages that include Estonian. But about the results. We can see that the amount of data beats the quality of the data, which means that more data is better, even if the quality is not that good. We can also see that manually fixing translation errors doesn't guarantee you better results. So is it worth to do it at all? And finally, it's more beneficial to use machine-translated data with multilingual language models because you can mix it with data in other languages, which is good because, as we know, more data is better. Now about translate test. To remind you, translate test means that the model is trained on English, and the predictions are made by machine translating test data to English before feeding them to the model. For the comparison, the slide also shows you the results from translate test experiments. You can probably easily see that translate test outperforms translate train by a large margin. And even for zero-shot results, which means that the model has not been trained for the specific task at all, are competitive. The zero-shot results are competitive with fine-tuned translate train models. So to conclude, the experiments showed us that machine translation is beneficial in situations with no data because it already can give us quite good baseline results. Secondly, we can use it to produce some results for natural language understanding tasks in Estonian and keep working from there. And thirdly, what's a bit worrying, or maybe not actually worrying, that's how you look at it or who you are, whether you are a machine translation researcher or natural language understanding researcher, is that translate test is a very strong baseline to beat. Why is it so? And is it true with every dataset? That's a question for the future. Thank you for listening.
Thank you very much. Questions? In your opening title, you had the goal to solve the natural language understanding problem, right?
Did I?
I think you had.
I don't remember.
So my question is, how far are we from solving
For Estonian
NLU?
Or for English?
Your task was for Estonian.
For Estonian. There's still much work to do. So
I like this goal for PhD student. Let's solve it. Why are you so shy asking questions now? Friends.
So, do you know if there is any research, maybe on other languages, that would look into whether this using what was the better one, the translate test, right? If that is affected by the fact that the original data set was in English and then translated back into English, if that it's like English specific data, if that affects the results, and if it were some data that originated from Estonian, it would be the other way around?
I don't know that there is any experiments, at least for Estonian, where the dataset originated from Estonian and it was translated to English, but that is definitely something to look into it, because it might give us different results. I mean, translate test might give us different results maybe.
Okay, and a quick follow-up, is the result similar, do you think, if the model that is fine-tuned is not multilingual, but just English language model?
Actually, I think one of the results that I presented, the model ESSCaSS was only trained on English, if I recall correctly, and it was not multilingual.
Okay, thanks.
I have another question. There is a tendency of languages to die out, like disappearing, right? And is it true that those languages that will get natural language processing computer support, these will not die out? Or what is the size of the language and the support of in the NLP? Do you have any feeling about danger of language dying out, going extinct?
Well, I think the NLP communities very much recently has started focusing on very small and endangered languages. And the general understanding is that, yeah, we should focus on these languages to avoid them to die or go extinct.
So Estonia is on a very safe side on that sense now?
I believe so.
Good. There is some reward at the end.
Thank you.
Okay, so if Novin ended with a controversial statement, let's see whether you consider I already start with one. So anyways, let's start with the analogy from computer science. Let's say you have a goal of you want to improve your task performance, and in a task called adding an element, let's say you have reached the limit to your limits, and so you can adopt an approach of upgrading your hardware, or you can adopt a software approach that you go from a not so efficient data structure to another one which allows that operation to be performed more easily. So in this case, going from an array to a linked list is better. Or you see that it really depends on the task which data structure actually helps you or not. So if your goal now, the task is actually accessing an element, then going from a linked list to an array is better. Okay, so to rephrase it, you can imagine that in the left side there's a bad performing hardware, and you want to move its performance to the same level or even pass the level of a better hardware. Yeah, and you can do it by adopting a more suitable data structure or algorithm, given that the better hardware is not using that. Okay, so let's switch to cognitive science. So you can imagine that there's a natural variation in people's born with abilities. You can be on the lower side or a high-end hardware side. And now that I ask a question, what can you do to improve your task performance in a digit span task, for example? A digit span task is where you're given one digit a second to memorize. And if you manage to do like 7 digits in a row, your digit span is 7. If you manage to do 8, then it's 8. An average person can do 7, right? But there was a researcher who paid a subject who was with an average IQ and otherwise average person to train the digit span for over the course of 2 years, 250 hours in total. And he managed to increase his digit span from 7, which is average, to 80. Yeah, you can imagine that. And how did he do that? He adopted a new way of representing, or adopted a new data structure, so to say, by not thinking about the numbers just as numbers, but numbers as running times, because he was a runner himself, and associated those running times hierarchically. Yeah? And since then, there have been 278 athletes who have reached a digit span of 80 or above, and the world record is 547. So there's 547 digits here. You can imagine, you receive them 1 digit a second, and you recall all of them. Yeah, quite nice. Now, how do these memory athletes usually do it is that they also have adopted a different data structure or a different representation for the numbers. So what they do is that they translate the digits into images. For example, 12 could be a plane. And as algorithm, sort of say, they use method of Loci. And for those of you who don't know what is method of Loci, it's basically a method where you imagine yourself on a familiar journey. This is, for most of you, a familiar journey in Tartu. And then you imagine the things you need to recall on that journey. And because you already have a very clear structure that you know, adding something that you don't know but want to recall later becomes super easy. So anyways, the point I'm making here is that it's not obvious that what is the different representation and what is the different algorithm to be used. If it were so obvious, there wouldn't be necessary to have that decades-long research also in computer science into data structures and algorithms. So, for example, how you could think about quantities. There's plenty of different ways. You can imagine it as a sequence of dots. So that's just representing 9, or the size of an area, or volume. These are non-symbolic ways of expressing quantities. So the quantity is the concept, but it can have multiple different representations. And there's also symbolic ways of expressing quantities. You can see the Roman numbers or Arabic numbers. And the point is that these different representations are not equal, but they have different properties. For example, only the Arabic number system has the property that the 3-digit Arabic number is clearly expressing a larger quantity compared to 2-digit number. It's not the property of a Roman number system. Yeah. So different representations exist. Yeah, we can add more. What's your bank card PIN? Don't tell me, but think about it. How do you retrieve it? I can imagine that most of you didn't recall the number, but you started moving your hand. Yeah? So that's another representation for the digit systems. I mentioned before that how the memory athletes usually memorize numbers is that they translate the digits into a different format, different representation, like a plane, and that different representation has different properties because it's not as abstract anymore. It's imaginable, and therefore it has a property of being more easy to memorize. Or these different properties also mean that they allow for different operations or different algorithms to be used. So please raise your hand who wants to make a sum in the Roman number system. Yeah, so it's weird, right? I mean, you can do it kind of, but you need to. It's much harder compared to the Arabic number system. Arabic number system, you can kind of ignore most of the data. You can just look at the one column of numbers and do the like a part computation at a time. So I already mentioned there are different ways to express the same thing. Like I mentioned, different ways of expressing the quantities. These different ways of expressing the same thing has different properties, as well as leads to different possible operations that you can do, or different algorithms to be used. And because it's not obvious what is the right or the best representation, but it rather depends on the task at hand, there's no best representation. There's no single best representation for any concept. Yeah? And because there's no single best representation, cognitive data structures or representations can be designed deliberately. For example, you can optimize for different things like memory versus compute trade-off. This is an example of multiplication table. Let's say you could either memorize all the possible different multiplications by heart. It requires a lot of memory and it requires a lot of training, but the advantage is that if it is actually committed to memory, then it's fast, the response, right? But on the other hand, if you want to optimize for the least possible learning time, then you just learn how to multiply, underneath each other, and then whatever number you receive, you can do it. You can optimize for the use of specific algorithms. For example, only visual representations allow them to be used in the method of loci. So you can't just imagine the Arabic numbers in Tartu. I mean, you can, but it's not going to be memorized as well. You can optimize for knowledge transfer, command line interface versus a desktop. I mean, when desktop came, people intuitively all of a sudden understood, what am I even doing? Or there's a lot of queues. I mean, the bin, you can throw bin files into a bin and then, or drop them there. It's intuitive. I mean, we've been dragging things into the bin since the dawn of time, I guess, or since the dawn of bins. But there's also the communication that you can optimize for. You can just send someone a CSV file, or you can send a line plot, or a bar plot, or a pie chart. I prefer the pie to be a dessert, but you choose for yourself. And that's it. Thank you. If there's no questions, I can ask myself.
No.
Yeah?
There certainly will be. Certainly will be. So you described that there are different representations. So what? How is that related to your research? What are you studying?
Thank you. So, what's the point? For example, we could rephrase the question into how to represent time, right? So, like there are different ways how to think about time, and time seems to be rather essential to our daily living. Thinking about time basically is a way how do we plan the future. And if we have a good way of representing the future, for example, a year or a week, then when we hear an event that we need to remember, then there's a slot in our head that we can immediately put it into, and there's no effort in memorizing it. But if we don't have a good system, then we can't memorize it. So my research is basically, I mean, the initial first paper is going to be about theoretical that that we should be open to designing new ways of thinking about even common things, like I mean, like the number system has you know, evolved over centuries and thousands of years, included the imaginary numbers and complex numbers, and it was a breakthrough in the concept, or like the adding a new representation led to solving a lot of problems which were problems only for the other representation, not necessarily for the complex number representation.
By the way, I have a feeling that your Roman numbers did not compute.
Which ones?
Your Roman numbers. Maybe in the auditorium somebody has to say. It's Roman numbers can't be just arbitrary letter sequences of L's and X's and I's and V's. You have to calculate that Roman number example.
You mean this one?
Yeah. Is it?
It's a bit touchy.
What is this X-lick?
It's 109 plus 49.
Is X-licks a number? Isn't Li 49?
L1 is 51 if it's independently, but because it's, you know, like, okay, we can, like, we can Google for the right representation for the 49 at one point.
Finally, we have some.
I have the mic already. Thanks, Tavi. I guess it was very, very abstract to many people, but knowing you, I know you have these encoders in your own brain as well, how to transform this number into some wacky picture. So could you give us like a small example of how would you remember the number 256 on the arch bridge or something?
6?
256.
256. So like, yeah, there's different ways of how to, I mean, 256 is just 2 to the power of, is it
But
8?
do it the right way.
Yeah, but okay, for computer scientists that might be it. But like, if the number would be something different, or like, let's say it's 256, then there's multiple different systems how to translate that into images. One thing that I can teach in half a minute is that I guess you can take the rhyming system. 2 would be shoe. So instead of 2, you imagine in shoe, and so the shoe would be on the bridge. 5 would be hive, dive. Yeah, like, okay, so you can imagine someone diving into the like a diver into the like a fountain. Thank you. And 56, 6 is sticks, for example, like the drumsticks. And then you can imagine someone playing like a heavy metal concert at why not Rammstein, as we were talking about, or Slipknot, the dead drummer who's was the world famous drummer, is giving a last performance there. So yeah, this way. So shoes would be, you know, like someone tying the shoelaces together, throws it up there, and does a few rounds over the bridge. Okay, I guess that's a bit more like a...
Sounds like information overload.
Yeah. So
What I wanted to comment was that this kind of last layer of when you have transformed it, it looks also very mystical and hard to understand, as in the machine learning models. So in that sense, there's a parallel, perhaps.
mm-hmm. I mean, as I mentioned at one point, that it's not obvious what should be the strategy, right? I mean, yeah, for those of you who haven't heard about any of those mnemonic techniques, for example, it's like, what the heck am I doing? Like, I mean, why wouldn't you just repeat the 256 in your head, right? But depending on your task, I mean, if 3 numbers is all you need to remember, I mean, then you can repeat it. But if there's 547 digits that you need to recall with a pace of 1 per second, then it's not possible. But it helps to know that it is possible with certain techniques. And I encourage you to think about, whenever you teach, for example, as well, to create, or like think like what are you optimizing for? For example, whether you are optimizing for the least prerequisite knowledge or not. So it could be that you're overloading the listeners, like possibly I did, with new information that you had no clue to like tie with your previous knowledge, and you could design a specific example or a representation. I hope that the analogy helps for you to understand. Anyways, thank you.
This is one big misconception that I have to explain to everybody, sort of like not from our field, that mathematicians and computer scientists do not calculate in their heads all the time. They don't memorize numbers. We don't do that. We have computers for that, and we think in slightly different manner. But
okay,
thank you.
Thank you.